Now that we looked at most of the common operations in CNNs, let's look at the different building blocks. So again, CNNs typically will use these operations in many ways that you can think of this like Lego pieces. And this concept will come up over and over, and you'll see in the architectures that we'll study later today that there are a lot of pieces that are very similar from architecture to architecture. So let's start first with going back again to why we're using CNNs. So our CNN can be used to map our inputs. So for example, an image, say we have the image of a dog, and we want to map it to a certain probability distribution. So if we know that there's a certain amount of categories that we want to classify this dog as, we want to be confident that our network has figured out that this image represents a dog. Right? So ideally, we have our image as an input. We have some kind of CNN black box, and out of it comes out some probability distribution. And if we consider the case of a color image, so we have 256 pixels by 256 pixels, multiply that by 3 channels, and that's a total of about 200,000 inputs. Right? So we have approximately 200,000 inputs that in this case we want to reduce to 3 inputs. So how do we go from this 200,000 inputs to approximately 3 inputs? And it turns out that there are many useful building blocks that we can use to do this efficiently. So this is what the most common set of building blocks looks like. And we're going to break this down into detail. So take a look at this image. There's a lot of operations going on. But again, most architectures that you will use typically look something like this. Some kind of convolution, some kind of nonlinear activation, and some kind of pooling. So let's break it down in detail. The first one is apply the convolution. So we take our kernel, we take our image, and we output some kind of feature map. We then take this feature map and we apply our nonlinear activation. So this is what gives our convolutional neural network its power, is that it's able to do these nonlinear operations on our feature maps. And these are typically applied element-wise. So you saw the ReLU yesterday, and again, there's different activation functions, and most deep learning frameworks implement most of the popular ones that are used. But typically, in the case of convolutional neural networks, you'll see ReLU or TANH being used. We then do the pooling operation. So we saw the max pooling operation. You can do average pooling, minimum pooling. It's kind of an architectural decision. But the pooling will allow you to reduce the size of your network. And this is really, I would say, the most common building block you see in convolutional neural networks. And what becomes your responsibility while you're building these architectures is to decide how you're going to piece these together. So you can have as many convolutions and activations chained together before you do your pooling. So here, for example, you can decide to do a convolution, a nonlinear activation, another convolution, another nonlinear activation, as many times as you want before you then do the pooling. And you can also decide the depth. So you can decide how many kernels you want at each step. And this is where this is going to change the type of architecture that you have. And not only that, but we can have many of these blocks chained together. So you can do your sets of convolutions and pooling, and then you get some kind of volume output, and that becomes your input into your next set of blocks. So you have, again, you just kind of chain them together more and more, and then you can build deeper and deeper neural networks. So this kind of allows us to go from arbitrary dimension to arbitrary dimension. If we take back our image, we do some series of convolutions and nonlinear activations. We pool. We then do that again, some series of nonlinear activations and pooling, and as many times as you want. And eventually, you get this output volume. So usually, we call this a feature map. And in this feature map, if your network has learned properly, you have a high-level representation of your image. So it contains a lot of rich information that's really hard for us to interpret, but that your network could then act to make decisions on. Now, if we want to get our probability distribution, we have to go from a volume to a one-dimensional vector. One way that you can do this is to flatten your volume and then use an MLP at the end. So this is a very typical scenario in some architectures that we'll see today. We do many of those building blocks that I've just shown you. We get some kind of volume as an output. We flatten our feature map. and then we use an MLP. We'll use a few fully connected layers, and then we can decide what is the probability in this case that we have a dog, a bear, a cat, etc. And it's typically, these fully connected layers are usually followed by a softmax, simply so we can obtain our probability distribution. So you saw the softmax yesterday in the tutorial, and this just allows us to guarantee that these results sum to 1, like a probability distribution should.